So hello everyone, welcome to Multimodal Weekly. This is a weekly webinar series hosted by the team at 12 Labs. We are an early stage, growth stage startup focusing on building multimodal foundation models for video understanding. We've been meeting weekly. We've been meeting on a weekly basis over the past year and a half or so. And here's some of the topics that we tend to cover on a weekly basis. New research in multimodal AI and foundation models. We have innovative application of multimodal in different verticals. Our community members go talk about the videos in multimodal projects, and then internal team member talk about how to use our technology. In some of the recent session, I've been inviting a lot of researchers working in this space. So you can see here some of the topics that we cover. Right? So things like benchmarking multimodal LLM to video retrieval to very heavily video-focused tasks like question answering, processing, segmentation, video LLMs, etc. So for the session today, super excited to have three presentations that focusing on different aspects of working with multimodal AI. So the first presenter is Benedetta Liberatori. I'm sure I'm pronouncing your name correct. Currently a PhD candidate at the University of Trento. She will talk called Test Time Zero Shot Temporal Action Localization, which dive deeper into her work. T3AR focus on as the name suggests, temporal understanding of action in videos. And then the second presentation will come from two PhD students at University of Maryland, College Park, Tianrui and Fuxiao, who will focus on hallucination benchmark. And they actually gonna give three separate, they're gonna present three separate papers that will kind of focus on hallucination benchmark. So yeah, excited to see how that can unfold. And then finally, we have Manjin, currently a PhD candidate at Pohang, POSTECH, which is Pohang University Science Technology in Korea, who focus on his new research paper that tackle attention mechanism for vision transformer. So yeah, so also a very exciting topic as well. So yeah, this is the quick logistical note for attendees. Feel free to send your question on Zoom chat, and then I can surface to the speaker, and then we'll have a Q&A session after the speaker finish. So with that, I will stop sharing my screen. I'll go unmute Benedetta, and then go ahead and share your screen and start your presentation.
So can you see my screen?
Yes, I can see it.
Okay. So hi, nice to meet you all. My name is Benedetta Liberatori, and I'm a PhD student at the University of Trento. So I will talk about temporal action localization, and in particular about this work that we presented at CVPR this year, Test Time Zero Shot Temporal Action Localization, which is a work co-authored by me, Alessandro, Paolo, Yiming, and Elisa. So first of all, we tackle the task of temporal action localization, which consists in localizing and classifying at the same time actions in untrained videos. So given a model, a video which is untrained, a model should be able to predict the start and end seconds of actions together with the corresponding action class label. And in the zero-shot setting, the action class labels are unknown at training time. There can be multiple occurrences as well within one video of different actions. So traditionally, zero-shot temporal action localization works train a model in a fully supervised fashion on a set of label data and then test it in domain. We believe these has two main disadvantages. One is the fact that, of course, they require a large collection of annotated data, which is quite difficult to have on untrained videos because they really require start and end seconds on long videos. it's really difficult to annotate this kind of data. But most importantly, the fact that this kind of models poorly generalize out of distribution, because we show with a cross-dataset experiment in the paper that this model learns some specific biases in the videos. Like, for example, on some dataset, there can be multiple actions, many actions within a video, or longer or shorter, and this kind of things. And this is like a normal course in computer vision and deep learning, but it's specifically bad for models and tasks that should be zero-shot. So what we want to do instead, we want to tackle a more practical scenario in which we assume we do not have access to training data for zero-shot temporal action localization. We got inspired by the test time literature, the standard one in the image domain, where the idea is that you, in order to perform a prediction, the parameters of the model are updated starting from an image and computing augmentations. The idea is that in a video, we have augmentations of images by nature, because we have an additional temporal information and we have many frames within a video. So we want to leverage this information, and basically we propose a method that instead updates the parameter, its own parameters at test time on a stream of unlabeled videos without prior supervised training. So in this way, we don't need training data to learn the task. So let's dive a bit deeper in the model. We propose this T3AL, which stands for Test Time Temporal Action Localization. And this model is built on top of a pre-trained vision and language model. So we use COCA in particular. For those of you that are not familiar with COCA, which comes from this paper, Contrastive Captioners are Image Text Foundation Models. It's basically CLIP with an additional text decoder, and it's trained with the standard loss of CLIP plus a captioning loss. So we start from the image encoder, the vision encoder, and the language encoder, and we use a compact representation of the video, which is the average of the embeddings of the frames within the video, to predict a video-level pseudo-label, which is a coarse-grained initial classification. So the idea is that we know that in general the video is about basketball dunk, let's say. Then we use test time adaptation to refine the predictions of the model. The idea is that the VLM, it's already good at classifying some of the frames within the video as a basketball dunk, for example, in this case, and also some other frames about something else. So we want to make the model overconfident, leveraging the knowledge that is already encoded in the model. So what we do is that we have we only update the parameters of the two projections of the two encoder, so this PB and PL that you see in the image, with a self-supervised objective. So the idea is that we take the frame within the video and we compute the semantic closeness to this pseudo-label for every frame. Then we form sets of positive and negative samples from those frames that are more closer or more distant in the latent space of the VLM. From these sets of positive and negative samples, we use a self-supervised loss, which is composed of a representation loss and a separation loss, to update the parameters of the model. So the representation loss brings the representation of the positive samples closer in the latent space. We don't want to push closer the negatives, because the idea is that negative samples are distant from the action that we want to localize, and they are like the background of the action. So they can be multiple things. And we don't want to push together in the latent space representation of images that may represent very different things. Instead, with the separation loss, we enforce the separation of the scores. So positive samples should have a score closer to 1, and negative ones should have a score closer to 0. Both these losses are implemented with a bio loss, which comes from this paper, Bootstrap Your Own Latent, NeurIPS 2020. And probably you know this loss. It's a commonly used loss in self-supervised learning. So once we have, after a set of a number of steps of adaptation, we perform a final prediction, and then we drop these updates. So in the end, the vision and language model, it's always the same. We just update on sample basis. Okay. So after the final prediction, we have a final step of, let's say, region suppression. So we remove some part of the predictions, and this is guided by text. So I told you that this VLM at the base has an additional text decoder. So the idea is that we start from the intervals that have been predicted. We caption frames within the intervals, and in this way, we want to use some information coming from the text without captioning the whole video, because untrimmed videos can be also very long. Instead, we caption only frames of the intervals that have been selected. We consider their textual representation, and then we compute the pairwise similarities of this textual representation of the intervals and the visual representations. The idea is that if once computed all the similarities, if interval has a textual representation which is not enough similar to the others, then it's discarded because it's considered as a false positive. Okay, so we evaluate the proposed model, T3AL, on two commonly used benchmarks for for temporal action localization, in particular in the zero-shot setting. So THUMOS14 and ActivityNet version 1.3. And we compare against both training-based approaches and some training-free baselines. So first of all, you can see that training-free baseline based on CLIP or COCA, for example, so starting from standard image-based VLMs, are perform really poor. The idea is that these models, of course, are not trained to localize actions within videos, but also these actions are very fine-grained. So it's very difficult for an image-based model to perform this kind of prediction. It's not just moving from image to video classification. Then even a very naive training-free baseline, so with this t = 0 means that we are not performing any kind of adaptation, we improve further. In particular, on ActivityNet, we see quite a big improvement, which is very interesting. And then we show also that with test time learning, we improve further. Of course, there is a gap with training-based methods, but this gap can be, let's say, closed somehow. So what we wanted to do after these kind of experiments, we wanted to check how can we fill this gap? How future work can fill this gap? So we performed some kind of oracle experiments, adding some partial information in different parts of the model to understand. First of all, let's say we start from this. Okay, I didn't say that the metric I'm looking at is the mean average precision. So it's the same situation for object detection, but considering detections in time. And we look at the average at different thresholds of intersection over union. So this is where we start from, these greenish, let's say, values. And then if we add a perfect classifier, so instead of computing our pseudo label of the whole video, we use a perfect classifier, we improve, but the improvement is marginal. This is because the classification part of the problem, it's already an easy part. It's quite solved. The localization part is the difficult one. Instead, if we consider to have the exact number of intervals of regions that we want to localize, still we have a minor improvement. So this means that more or less we are, let's say, predicting already the good number of intervals within, of action intervals within videos. Instead, the big improvement is given by this constraint boundary selection. What does it mean? So in this constraint boundary selection, we select the positive and negative samples within the ground truth intervals of the temporal action localization annotations. So this means that if we have maybe better heuristics of for the selection of positive and negative samples, which is they are fundamental then for the self-supervised objective at this time. or if we have like a better vision and language model at the base or something like that, this can really be improved. And if this is done, if just this adds 7 points, then it means that the adaptation can be taken like for longer, for more steps. And if we consider all these things together, we have we basically match training-based methods, which is this line here. So this, of course, is not to say that we are on pair, but it's to say that training data is not necessarily fundamental, let's say, and that this kind of approaches, so let's say instead of let's say adding more compute at test time, can really be like a solution for this kind of tasks. We also have some qualitative results, and you can check the website of the project of the paper to see more qualitatives. But it's just to show that this kind here you see like a similarity with the ground truth, which is also the predicted class, and also the ground truth intervals and the predictions. So these models have really like a lot of actions, occurrences within the videos, and they're let's say already this kind of adaptation really gives like some good results in this sense. So we have very low similarity outside the ground truth regions of the actions. So to summarize, with this work, we first highlight a shortcoming in existing zero-shot temporal action localization approaches. So the fact that they are trained in theory to perform this task on untrained videos in a zero-shot manner, but in the end, they really struggle to generalize out of distribution with a simple cross-dataset experiment. And then we propose this method, which takes a generic vision and language model, and it adapts it at test time on two things. Let's say we start from an image-based model, and we adapt it to video data. But most importantly, we adapt it to actually learn a task. So we learn the localization task at test time in a zero-shot manner and without training data. And our evaluation, our results, and also the Oracle experiment shows that this kind of adaptation at test time is a promising direction to calibrate, to adapt vision and language models, not necessarily on image, let's say, task, but particularly on videos. And we believe that this can be scaled also to different kind of tasks like this on untrained videos. So thank you for listening, and you can check, the code is available. You can check also the original paper, and also on the website there are additional qualitatives and informations and things like that. So thank you again for everything. If you have questions, I'm happy to take it.
Awesome. Thanks, Benedetta. Thanks for the walkthrough. Yeah, for the audience, do you have any questions for right away? Maybe just one question from my end, just to get a quick start. So you mentioned you adopt the COCA model as the vision language model, right? And the reason for that decision, and you know, with any other candidates that you consider?
Yes. So the main reason is the fact that we want to like maintain everything more compact. So the idea is that we start from a model, and in the end, we always use the same model. Even if we adapt, we discard the updates. And since we wanted to use also some information from captions, and we didn't want like an additional model, but the same can be done with Clip plus an additional like off-the-shelf captioner. We just wanted to maintain everything within the same model. This is very lightweight. You just need one model that can perform both things. So the standard like similarity like prediction plus the additional captioning. So this is the main reason, but of course this can be like adapted to your favorite vision and language model plus an additional captioner, of course.
I see. So you actually need an additional captioner.
No, because Coca is like, it's basically like Clip, like two encoders, okay, plus a text decoder. So it's like it's in the end like from the same model trained jointly. So it's not trained in two steps. So this is more or less the idea.
Got it. Maybe other, audience, if you have a question, please put on the chat. I think another one that I have is around getting this video pseudo label, right? I think that's step number one of your. If you don't mind, I can quickly share that screen again. The screen,
Yes,
the slide where you have the
sure.
4
I'm
steps.
gonna share it again. Yes, sure. Okay, so this one. Yes.
And the encoder here is from Coca, right?
Can you repeat the question again? So this is the
so the purpose of getting pseudo label is to
okay. So
people can explain like the purpose of
sure.
getting the pseudo label would be great.
So the idea is that in a video, let's say, maybe I can also go back on this, we want to localize, for example, where in the untrimmed video the basketball dunk is happening, you know? So in general, the video would be about basketball or something like that. And we want to localize where basketball dunk is happening. So the idea is that the original, the initial part gives us a coarse-grained classification. So we know then after this that the video is about basketball dunk. And then we go on refining this prediction, exactly localizing where in the video the dunk is happening. So this is the pseudo label, let's say, initial part. The idea is that we understand what we want to localize in the video given the set of actions.
Got it.
Okay.
Yeah, I think that's super important. It's a very clever way of getting like the crowd truth label for the next phase of the workflow, right?
Exactly. Because the idea is that then we want to refine this and, okay, the whole video is about basketball dunk, but then we want to understand exactly that here there is the dunk and not in the whole video, of course, because the video is untrimmed, not like trimmed videos for video recognition or video text retrieval or text video retrieval. It's more like it can be longer and we want to localize exactly like the seconds in which something is happening.
Got it. Maybe just one final question from my end before we move on is, I think maybe you already covered this in the future direction, but like, what would it take to improve the performance of this approach? Would that be better base model?
Okay.
Would that like new novel ways? Yeah. What are the consideration?
Yes, sure. So in my opinion, like we really see also from the results that the adaptation is really adds on top of a standard training free approach. So we see also that going on with the adaptation, we gain numbers, we refine and obtain better results. So in my opinion, given that here everything is unsupervised or self-supervised, better, because of course, given it's at test time, we cannot access ground truth labels of any kind. So this really relies on this step, which is the formation of positive and negative samples. So the idea is that we want to leverage the frames, the parts of the video on which the model is already confident that that part is the action that you want to localize and that part is like the background of the action, something that you don't want to have. So this selection is something that like if the selection is wrong, then the model is optimized at test time with a wrong objective. if this selection list is good, then the model is optimized with a like the right objective, and the final prediction is good. So to me, probably this thing, like the selection of positive and negative samples, then this, of course, can come also from a better backbone, because the idea is that, of course, the more the backbone is already encodes knowledge about different actions, the better than the selection of positive and negatives and the final adaptation.
Yeah.
But to me, this is like the most important part, and it's also where we see the major improvement in the Oracle experiment. This is also why we wanted to add that experiment to show this is a promising direction.
Awesome.
Also, as I was saying, like for different tasks, so not necessarily temporal action localization, but could be also other tasks on videos, on untrained videos. Because again, the idea is that we want to leverage test time and the fact that we already have augmented views of different frames, because we have many frames in a video.
Yeah, absolutely. There's multiple different other tasks that would be relevant for using this approach beyond action localization. All right. Yeah, thanks a lot, Benedetta. Really impacting in-depth presentation, and super excited to see some of the work in the future coming from your team as well. I know that University of Trento is pretty well known for like multimodal AI video understanding, right? So I keep seeing like a bunch of papers from your university at different conferences, so that'd be exciting. See it. Yeah.
Yes, super nice place to work, to be honest.
Awesome. Okay, so Tianrui and Fuxiao, I just unmute both of you. You want to go ahead and get started?
Oh, hey, can you hear me?
Yep.
Oh,
can hear you.
Give me 1 second.
And yeah, Fuxiao, you want to open up your camera as well so people can see you.
Oh, yeah, sure.
Can you guys see the screen?
Yes, I can see it.
Yeah. All right, so hi everyone, my name is Tianrui Guan, a PhD student at UMD, College Park. Fuxiao Liu, who is also a PhD at UMD. Together, we will present our work on hallucination benchmark curation mitigation for VLM. So excited to be here. We will present 3 works: HallusionBench, AutoHallusion, and Eagle. So the first work we will present is HallusionBench, an advanced diagnostic suite for entangled language hallucination and visual illusion in large vision language models. This work is accepted to CVPR 2024. There are 3 main aspects I want to talk about in this work: the data, benchmarks, and...
Just one note, Andrew. I think you're still on the first slide. I didn't see the transition.
What about now?
No, yeah, now it's it.
Oh, great. Sorry, give me 1 second. All right. So first, we introduce HallusionBench, the first advanced diagnosis suite tailored to systematically diagnose and the diverse failure modes of large VLM. HallusionBench consists of approximately 1,200 visual question-answer pairs, featuring 165 images originally from the internet and another 180 images that are edited based on those original images. We evaluate 15 most recent methods on HallusionBench, including GPT-4 Vision, Gemini, Pro Vision, Cloud 3, Lava 1.5, etc. In addition to correctness and accuracy, our VLM pairs are thoughtfully formulated with an innovative structure, which allows us to quantitatively analyze different aspects where the current model fails. And finally, we explore HallusionBench and provide an in-depth analysis on examples on which the SOTA large VLM fails, such as GPT-4 Vision and Lava 1.5. So first, the dataset consists of yes/no question pair with or without visual. Our VQA pair by design consists of visual dependent question and visual supplement questions. So for example, in visual dependent question, the question is asking for some information in the figure, like are two items are of the same size or are the two lines parallel with each other. Therefore, the answer could not be specified without the images. And on the other hand, in visual supplement questions, the questions can be answered without the visual by using common sense, but the visual information can be supplied to facilitate the question answering. So as a benchmark data set, we design different types of accuracy metrics to evaluate the correctness of the model. I will not go into much into detail about this since it's pretty standard. I want to highlight our benchmark as an analytical benchmark such that it can expose different failure of the models. For example, something we know widely exists in most VLMs is tendency to answer yes or give affirmative answer. We call such failure yes/no bias. We designed metrics to measure how likely the model wants to answer yes. The first measures the difference between the number of produced yes and actual yes. And the second one measures the percentage of yes outputs out of all incorrect answers. And secondly, we also want to measure the consistency of the model. Basically, we want to make sure that among the answer to several questions, there are no contradictory output. So for example, in the slides, given one image and several questions, we wish the model to say yes to only one question and no to the other two. Otherwise, the model is making contradictory claims and could be making random guesses. So we designed this figure accuracy to measure logical consistency of the model. And finally, we want to examine two failure components of the VLMs. To facilitate this, we give the definition of language hallucination and visual illusion. So language hallucination refers to the perception formed without relevant visual input. In language hallucination, the model makes false prior assumption about the input and the visual context based on its parametric memory. The model should respond based on how the question is framed instead of ignoring it or make false assumption about the image. Visual illusion denotes the misinterpretation of accurate visual information. Visual illusion comes from the failure to recognize and understand the input image visually. The model could not obtain accurate information or reason about the image correctly. So now let's take a look at some examples and analyze by case. So this is an example of language hallucination. Based on the response to the left image, which is originally from the internet, we know that GPT-4 Vision has the answer and know it's a well-known illusion figure. It answered correctly based on the parametric knowledge. And after we modify the image and make the bottom line longer, GPT-4 Vision still gives the same answer. Therefore, we know the model is using its parametric knowledge and gives a biased response. So it's very likely to be language hallucination. And in this example, we show two perpendicular lines and GPT-4 Vision gives an incorrect answer. We know it's not likely to be in parametric knowledge since it's just a vertical line and horizontal line. But now let's look at this example with another question. We put it on the left. So in the image on the left, the model can recognize the two lines are of the same length. So therefore, we are more certain that the example on the right gives an incorrect response due to visual illusion. So basically, with paired question, we understand the failure better. Now we see two cases by reading through the example. However, we want to automate this process. And to do that, our data is structured in pairs so that we can do a better job using logic and a few heuristic to build a decision tree. So for example, in this example on the left, the model does not know the answer to the question and gives an uncertain answer. But after giving the chart, the model gives an incorrect answer so that we know that the failure is within its visual encoder and it's due to visual illusion. So basically, we designed this decision tree and use GPT-4 Vision with proper prompts and instructions to parse the VLM outputs and the actual answer and generate whether the response is correct or not. I will not go into detail about the tree, but we've given several example pairs and show the corresponding decision path. So please refer to our report starting page 30. And this is our leaderboard. Notably, the SOTA GPT-4 Vision achieves merely around like 30% question pair accuracy, while the performance of other method falls below 16%. So our benchmark poses great challenges to existing VLMs. In addition, I want to highlight that the evaluation by hand and by GPT-4 Vision on the first few rows shows that our GPT-4 assisted evaluation is fairly acceptable. And in this analytical leaderboard regarding yes-no bias, consistency, as well as the language and vision diagnosis, we can see that GPT-4 Vision also have the best and most stable performance. A very competitive model, Lava 1.5, suffers a lot from yes-no bias. Additionally, visual illusion is the predominant issue in most VLMs. Finally, here's a couple of takeaways. First, parametric knowledge sometimes overtakes the visual features. The model should handle the trade-off between the parametric memory and context better. Secondly, there is no parametric knowledge. When there's no parametric knowledge, the model still suffer from visual illusion. The visual capability of existing large VLMs is still very limited. Thirdly, the model can be easily misled by simple image manipulation like flipping, rotation, auto reverse, etc. And finally, the model could not handle temporal relationship very well. The second work I will present is AutoHallusion. This work is recently accepted to EMLP 2024. Compared to last work, instead of manually select and edit the image to induce and analyze hallucination, we want to automate the process of generating VQA pairs so that the model could be more prone to hallucination given those cases. With this automatic pipeline, we can tailor VQA pairs that are challenging to specific VLMs, and the number of those difficult cases can easily scale up. Those data can be used later to analyze the model or mitigate hallucination through fine-tuning based on their vulnerability. So our contributions includes an automatic pipeline. Basically, we propose the first automatic hallucination generation pipeline utilizing 3 image manipulation strategies. We also propose a method that probes and investigates contextual bias in the language pair, which is the cause of the hallucination. And finally, we evaluate the SOTA large VLMs, including GPT-4 Vision, Gemini, Cloud 3, Lava 1.5, on benchmarks by AutoHallusion. It achieves success rate of 97% and 98% of inducing large VLM hallucinations on synthetic and real-world data. So the intuition of our work actually comes from some concept in the field of cognitive science. First, I want to introduce the term schema. Schema refers to the tendency of human to organize information and interpret the world based on patterns of past experience. For example, it's far more common to see a keyboard and a mouse in front of a monitor instead of a cooking pot. So creating irregular schema can lead to cognitive dissonance, while breaking a schema result in expectancy violation, both of which can induce contradiction and discomfort in memory. So we believe that human cognition and memory share certain similarities with large VLMs in these aspects. As a result, we developed 3 strategies focused on creating irregular schema and breaking existing schemas, which in turn leads to VLM hallucination. So here's the overview of our automatic pipeline. To induce hallucination, first we prepare a list of things and objects as raw data to construct the vision question pairs. So the things and objects are either from generator model or existing datasets. Then we probe the large VLMs to determine how to manipulate those images and construct the questions around existence or spatial relationship of the objects. We will also obtain the ground truth about this image after those manipulation. And finally, we have two metrics to determine whether hallucination occurred. I will go into detail in the following slides. So there are three main image manipulation strategies: abnormal object insertion, paired object insertion, and correlated object removal. In the first strategy, we are trying to insert an out-of-context objects to create an contradiction and discomfort of the scene. And in the second strategy, we find a correlated object pair, for example, a keyboard and a mouse, and only insert one of the objects into the scene. And in the last strategy, we remove one object from the scene that are strongly correlated with other objects within that scene. So the questions are formulated around the manipulated objects or the object of interest. We mainly ask existence questions or spatial relationship questions. So to determine which object to add or remove, we prop the large VLM to determine what kind of object to insert or manipulate, or which object to remove. A different large VLM may have different preferences, so our manipulation is also tailored to specific large VLM. Exploring the vulnerability of specific VLM and create a tailored data could potentially be useful for further fine-tuning and improvement. To evaluate and determine whether hallucination occurred, we use correctness and consistency as metrics. To better visualize it, here I give a few examples. On the left, the answer does not align with the ground truth. And on the right, the response to slightly altered questions is inconsistent with the answer to the original question. So the consistency metric is useful when we attempt to add or remove an object but failed, leading to misalignment between the image and the ground truth. So here's the result from our automatic pipeline for generating hallucination. Each of the manipulation strategies is effective in inducing hallucination. And given limited time, I will I will refer you to the paper for more results and examples. Our code and demo is also available in the following GitHub link. So please follow up on Twitter for more updates. There are a few things to improve the current work. We plan to improve the quality of the edited image. In addition, we plan to use generated data to fine-tune the model and improve its performance. So now I'll hand the stage over to Fuxiao, who will present his work on mitigation.
Hi guys. Okay.
Do you want to share?
Yeah.
Wait. I'm okay.
Okay. Can you see my screen? It's the Eagle exploring the design space for multimodal large language model. Can you see my screen?
Yeah, I can see it.
Yes, I can see it.
Okay. Okay. Cool. Okay. Thanks for Tianrui to present the HallusionBench and AutoHallusion, which design the excellent benchmark to evaluate hallucination of multimodal large language model. So I will talk about our new model, Eagle, exploring the design space for multimodal large language model with mixture of encoders to solve the hallucination problem of multimodal large language model and improve the ability. And this is a collaboration work with NVIDIA, UMD, and also Georgia Tech and HKPU. So generally speaking, our exploration include the three steps. The first one is that we will try to increase the resolution of image, which is usually a way to solve the hallucination, which allows to increase the perception ability of the model. And then we also try to include more vision expert, not only include like the object detection model, maybe like the Dano V2, and also maybe test recognition model like Pixel Struct, and also like a segmentation model like SUM. And the second, we also try to analyze, how can we, feel the, the different vision encoders and we try to analyze, maybe the sequence append, or maybe like a channel as concatenation, and also maybe mini Gemini style, and also maybe like the deformable attention. And also after that, we also analyze, the pre-alignment strategy, which is kind of, also improve the model stability. And finally, we'll try to analyze, the how do we, select the X, because there are many vision experts right now. Maybe not only we have like the SUM, Dino V2, Pixel to Struct, but also maybe other experts. So how can we select maybe the most correct, maybe the best combination of different experts? So I will talk about it one by one. So the first step is like the stronger vision encoder, which is like a general conclusion. You can see like you can see in the chart, in the first column we have like the different method, to increase the resolution. Maybe include like the original, means like the original clip encoder. Like the resolution is 336. So in order to increase the resolution, we use like the two methods. One is like interpret it, and also it's like the tell input. And also you can say like we will try to compare, we compare with like a unfreeze vision encoder and also freeze the encoder during the training. And you can say after looking at the table, we can find like unfreeze the vision encoder and also increase the resolution can significantly improve the performance. You can say maybe just like the raw in the right box, you can say it achieves like a very similar result with like InternVL. You can say, but for InternVL, you can see the number of parameters is much larger than our clip-based model. But you can see the average score. Average score means we calculate the average score of like 15 multimodal large language model benchmark. And you can see like compared to InternVL, our fluke value is smaller, and also the number of image we can process in each second is much larger than InternVL. So you can say we choose the setting in the right box in the future experiment. So after talking about the resolution increase, we also analyze how can we try to extend to multiple vision expert. And you can see in the chart, the CL means clip, the CM means cover nest, and also DI means Dino V2, and SE means like sum, and PS means pixel to struct, and EV means ever detect V2. And you can see in the table, like generally speaking, if we increase the number of the vision experts in our model, the performance will increase a lot. You can see if we choose like equal X5, means like we have like 5 experts, the performance will have like the higher score in the accurate average score. But you can see when we have like six expert, the performance may reduce a little bit. So we can say like maybe for the number of 5 experts will be like the optimal like number of experts. Then like we have like several experts, maybe like we have 5 experts right now. So how can we how can we how can we combine this every expert? So here we try to analyze like can see like 5 different fusion method right here. As you can see like in the chart, our experiment start from like vision equal X2, means like we have only have like 2 vision encoder right here. You can see like we have like the clip or clip plus cover nest. You can see like in the chart, although you can see the sequence append achieve the higher score in like if we only have like 2 vision encoder. But you can see like compared to the channel concave, you can see the parameter size and the number of tokens it can process each time, does not perform better than the channel concave. So also you can see like if we change the number of vision expert to 3, you can see like the channel concave achieve the best average score, and also like the smaller number of parameters, and also maybe you can see can process more tokens in each second. So we can say that that channel concatenation is the best way to combine different vision encoders. So we also propose like the vision language pre-alignment strategy. You can see for here for the figure right here we have like a three stage, like stage 1, stage 2, and stage 3. And if you look through into like stage 2 and stage 3, you can see it will be very similar to the LaLava paradigm. You can see like the stage 2 is like a pre-training strategy. We only train the projector or maybe the vision encoder during the pre-training strategy, but during the fine-tuning stage, the stage 3, we will train both all the vision encoder language model and also the projector in the training in the SFT stage. But we introduce like the pre-alignment strategy, the pre-alignment stage before the pre-training stage, which means that we'll individually train like each vision encoder with like a Vacuna 7B, which means that we'll try to transfer the knowledge from the vision from the vision part into the vision VL part. You can see the result in the table below. You can see if we combine like with like a clip with other different experts, like maybe for some pixel to struct and ever detect, you can see the best setting will be like unfreeze the vision encoder during training and also like doing the pre-alignment. You can see which the average score can achieve the higher score. And also we also try to evaluate the optimal training strategy. You can see like we do experiment like with like if we maybe like in SFT state we train for 1 epic or maybe 2 epic, or if we know like whether we do the pre-alignment and how can we choose maybe the dataset for the pre-alignment and the dataset for the pre-training. And finally we found like if we do the pre-alignment, but for the pre-alignment stage we use both the LaLava 595K dataset and also like Eagle 1.8 million dataset for pre-alignment and pre-training. But for the fine-tuning stage, we only use like Eagle 1.8 million data. And we also unlock the vision encoder during the pre-training stage. So you can see the last line is the best setting, and in the final experiment, we'll use this setting to compare with other models. So after talking about all the strategy, we maybe like increase the resolution, and also you can see use the pre-alignment strategy, and also maybe like maybe you use like channel concate to combine the different experts. We finally have like Eagle X5. You can see compare with a comparison with like which is the best open source model which was recently released by NYU from Sanning Xie. And you can see compared to comparison 1, our Eagle can achieve the better score on all of the benchmarks, not only include like the knowledge benchmark and also like a general benchmark and also like OCR and chart benchmark and also like the vision centric benchmark. So which and both we compare with them in both like for LaLama 38B and also like Vacuna 13B and also like E34B. So which demonstrate the ability of like Eagle, the ability of Eagle. So and also you can see like some examples from demos from like our Eagle. You can say like our model can not only can deal with like the chart, maybe like for the document, and also maybe for some like handwriting like chart, but also you can see our model can also deal with like maybe some like knowledge based maybe like just like the first example here is from MMMU, is like the college level knowledge, and also our model can understand. You can see like maybe the multiple image, and also like you can see maybe the image right here. You can see like which is about like a math knowledge. So you can see our model can handle both like the OCR task and also like you can see for the knowledge and also maybe for other multiple image. So if you are interested in our model, in our Eagle model, you can click into our GitHub star right here, which has already have like a 500 star right now. And also you can also try our like Hugging Face demo, which is like very interesting. Okay, thank you. Do you have any questions?
Awesome. Yeah. There was one question from Manjin in the chat, but looks like it has been answered already.
Oh, let me.
So I'll also unmute Tianrui if you want to just quickly answer it in
Yeah.
real time.
Yeah, so basically, yeah, Manjin, I think you raised a valid point. So basically, we try to use more advanced, more natural way to insert the object, but it turns out that it's not as stable. And so we end up doing is to either generate the object itself or maybe cropping out some objects from existing data set and then just paste it onto the image, so that at least we can make sure the object exists in the image. But for object removal, we are able to use in painting and create very natural image. But yeah, I think next step is what we're trying to do is trying to improve the quality of the image, either in terms of make it more natural, and maybe somehow we're also considering adding some layout to the object arrangement so that it's not as unnatural as what we currently have. Yeah. And so that's basically what we're trying to do in the future. Yeah.
Awesome. Yep. I hope that answers your question. So in the interest of time, I think we're running a bit over. We still have one more presenters left. So yeah, if you have any more questions for Tianrui and Fuxiao, please put them on the chat. And yeah, I'm going to unmute Manjin. And yeah, you can go ahead and present the final talk with the webinar.
Thank you, James. Can you hear me?
Yes. Can you share your screen and
PPT as well?
I can show you. Yeah. You might also like turn on your camera just so people can see the speaker.
Yeah.
Yep, I'm seeing you.
Yeah.
Go ahead.
Hello, everyone. So I'm Manjin Kim. I'm PhD candidate at Pohang University of Science and Technology in South Korea. So today I am very happy to present my recent work, learning correlation structures for vision transformers, which was published at CBPR 2024. So this work is done in collaboration with Paul Hong-seok, Correlation Unit, and Ms. Cho. So as you can see from our title, this work focuses on the correlation structures and enhancing vision transformers to leverage such correlation structures for the better visual representation learning. So
by the way,
this end,
yeah, you still at the first slide. It's not moving.
okay, sorry.
You still at the introduction, the outer slide.
Yeah.
Oh, you can just try to get him because I'm not. Right, go ahead.
Yeah. So to this end, so I'd like to begin with explaining what the correlation structures are and what information they could provide for the better representation. So in this work, we define a similarity between two tokens as correlation. So here I've sampled a query token for each image and video and visualize its correlation map. So these maps essentially show how the query token interacts to other visual tokens. So one thing to re-emphasize is that the correlation maps effectively suppresses some photometric information such as colors or textures, but it reveals relational information such as object layouts or motions in images and videos. So learning visual representations based on such relational information enhances generalizability across some challenging appearance variations or domain shifts. So as shown in the previous slide, so we humans easily recognize visual layouts or motions from these correlation maps. So my question is, how can we do that so easily? I believe that it is because we humans view these maps globally, and we then inherently extract some spatial patterns from those correlation maps to understand some visual context of these correlation maps. So we humans do not just focus on individual correlation values, but we use some broader spatial patterns of the correlations. So we call these spatial patterns as correlation structures. So in this project, our goal is to inject this rich correlational structure information into the self-attention mechanism, so we can improve the vision transformer, making them more structure aware. Now we then have to check if the self-attention already captures such rich correlational structures during the visual representation learning. To this end, I break down the self-attention equation into a form of summation of the weighted values. As you can see the equation, the self-attention mechanism transforms the query token into more visual semantically abstract feature by aggregating the related values based on a single pairwise quirky correlation. What we pointed out as the limitation of the self-attention in this work is that self-attention generates each attention weight based on individual quirky correlation only. So this means that they are blind. The self-attention is blind to the spatial patterns presented in the correlation maps when generating each attention weight. So to address this, we improved the self-attention mechanism to incorporate rich correlation structures in attention weight generation mechanism. So self-attention can consider rich structural information when deciding which value token is worth to be aggregated. So in this work, we propose a novel self-attention mechanism called structural self-attention. So it is designed to leverage correlation structures for feature transformation. So different from traditional attention methods, our methods detect some structural patterns across the entire correlation map during the attention scoring. So structural self-attention consists of two sequential steps. First, the correlation pattern detection and contextual value aggregation in the following. In the first step, the correlation pattern detection step, we simply apply a convolutional operation on top of quirky correlation map, and we then apply a softmax function on that. So here, the convolutional filters in UK serves as correlation pattern detectors. I mean, it extracts various and diverse local spatial patterns from the quirky correlation map. So in this figure, we extract 4 number of correlation structures. So I visualize the extracted 4 spatial patterns here. So we can easily observe that the correlation pattern detector UK learns to extract various and distinct and useful correlation patterns such as ears and mouth, eyes, mouth, and overlay. So given these diverse correlation structure patterns, so next thing we need to do is to generate some attention weights based on these correlation structures to aggregate the value tokens. So in the following value aggregation step, we pass the correlation structure tensor through a linear layer UV to obtain a attention scalar weight for each dollar token. Here, we call this linear layer UV as a context aggregator, since it combines all the extracted correlation structures to generate a dynamic scalar weight for aggregating each value in element-wise manner. We further extended these element-wise value aggregation methods into some chunk-wise manner. So here, the linear layer large UV generates dynamic spatial kernel, such as in this figure, 3x3 kernel for each position. So instead of generating a single scalar attention weight, this matrix, this linear layer generates a spatial kernel for each position. So, and these kernel weights are used to aggregate local chunks of values here, as you can see. And so we can obtain more contextualized output from the attention mechanism. So I visualize the obtained dynamic kernel weights here. So in this figure, you can see each small cell illustrates 3x3 special kernel weights for each position. So as you can recognize, our method adjusts the kernel weights dynamically based on the local correlation structures. So in this work, we also provide an in-depth analysis on the role of the convolutional projections in self-attention mechanism through a lens of a correlation structure modeling. Several modern vision transformers, such as convolution vision transformer, pyramidal vision transformer, multi-scale vision transformers, and so on, have achieved great success in computer vision by using a incorporating a convolutional operation for query key value token projections before the self-attention. So through our in-depth analysis, in our paper, we figured out that the convolutional projections for keys and values also serves as also act as a correlation pattern detector and context aggregator as well, similar to our method. So in conclusion, they do leverage correlation structure for visual representation learning. However, we figured out that they are still limited in capturing only one correlation structure, whereas our methods captures multiple patterns and use all of them for visual representation learning. So I omit the detailed explanation and proofs in this slide, so please refer to our paper for detail. So we compare attention weights from vanilla self-attention and self-attention with convolutional projections on keys and values and structural self-attention. As shown in these figures, the self-attention with convolution projections generates almost similar kernels across different positions, as you can see. So we conjecture that this is due to the lack of diverse correlation structure patterns. On the other hand, our structure self-attention dynamically generates a distinct kernel weights dynamically for each different positions. Since these 3x3 kernels are overlapped to each other, so we can aggregate all these kernel weights to form a single attention map as shown in this figure. So one interesting thing we observed that is that our method effectively distinguishes different object parts and dynamically adjusts some, how can I say, aggregation strategies according to the object parts. So as you can see in this ostrich image, our method effectively distinguishes ostrich heads from its neck, and our method effectively changes some aggregation strategies according to these object parts. So this is quite interesting to me, and this is an emergent property of using the correlation structures. So through our quantitative analysis, we also confirmed that using correlation structures improves both image and video classification accuracy. So we measure top 1 accuracy on ImageNet-1K and something V2 V1 dataset, which is a motion-centric video benchmark. For the experiments, we adopt DIT architecture as a backbone and then replaced all the vanilla self-attention blocks by our structured self-attention blocks. So the first plot indicates that using more diverse correlation structures improves both image and video classification accuracy, as you can see in this plot. And the second plot shows that correlation structures within larger extents improves the accuracy on both classification tasks. So these observation studies demonstrate that correlation structure modeling is quite beneficial for visual understanding. We compare our methods to previous state-of-the-art methods on both image and video domain. So here we use uniform as the backbone. So in image understanding, across image classification, object detection, and instance segmentation, and object segmentation, our method consistently improves the performance on image understanding. And we also shows, our method also shows significant improvements in video classification across various benchmarks, such as appearance-centric benchmarks, such as Kinetics 400, and also in performance improves in the motion-centric benchmarks, such as something V2, and Diving 48, and Manjin. So we say that the consistent improvements across various tasks and domains demonstrate the generalizability and effectiveness of leveraging the correlation structures. So in conclusion, our work highlights the importance of correlation structures in vision transformers. So correlation structures effectively reveal relational information such as object layouts, motions, and visual input. And the correlation structures are quite beneficial on both image and video understanding. And lastly, but not least, the capability to identify different object parts emerges with the use of correlation structures. So this is the end of my presentation. So for more detail, please refer to our paper through this QR code. Thank you for your attention, and I'm very happy to take any questions.
Awesome. Yeah, thanks a lot, Manjin. Thanks for going over it. Because we like pretty much over time, I think we can probably take the question offline, maybe via email or other channel. So yeah, for the audience, if you have any follow-up question from Manjin, I think it's best to just email him after the call, and yeah, you can ask him synchronously. Awesome. So with that, I think we can conclude the webinar. So I just want to say thank you to the speakers, Manjin, Benedetta, Tianrui for presenting today. I know it's going a bit longer than expected, but obviously there's a lot of content that we need to cover. Yeah, so thanks again for preparing the content and presenting to our audience. The webinar recording will be available probably within a month or so, and I'll be sure to share the YouTube link with all of you so that you can circulate that within your academic network. Yeah, and again, we run this series on a weekly basis, and we will file this content interesting and relevant. Would love to see you come back in the future. Awesome, guys. I will stop the recording and hope you have a good rest of your weekend.
All right, thank you. You too.
Thank you, James.
Right, thanks, Tianrui. Thanks, Manjin.
Thank you very much. Bye.
Bye.